And I'm going to superimpose on that, in inverted colours now, the comet's tail running from Land's End to John O'Groats. I was a bit nervous when I first put this together because, you know, there was a fear that that bit at the top might belong to a different country by the time I go. So bear that in mind. That's imagine that comet tail goes all the way across the British Isles. Then the object that's making all that stuff is about that size. In fact, that's an exaggeration. It's more like that size. And that is a shape model there of 67p. And if you're interested, that's the ESA project scientist and the lander manager having some fun at the comet arrival press conference. So think about that. You've got something that big that's making that huge tail. The huge tail you can see from Earth. But in actual fact, what we're interested in doing is going and finding out what it is that's making that tail. And that is quite a small object that actually is about something like 3 or 4 kilometres across in actual size. As I say, the theme is, what is life? Oh, no, the theme is life. And so I thought I'd introduce my talk by kind of, by tackling the question, what is life? And I'll start by showing that. Some of you might recognise that. This was a feature that was found in a Martian meteorite almost 20 years ago that was at the time interpreted as a biological fossil. So this was evidence for life on Mars. 20 years later, I can tell you that minds are very definitely made up, but opinions are still divided. So after all that time, with the world's experts looking at this, we still can't agree on exactly what that thing is. So that shows that it's a difficult issue. But when I want to know about things like this, I go back to basics, and I went back to S104. It's our excellent introductory course to science, exploring science. And in there, it has some definitions of life. And this is what you learn at level 1, university science level. So what is life? It's a state of being alive. Yep, I kind of quite like that one. It's the sum of activities of plants and animals. Yeah, right, whatever. And it's the period between birth and death. I mean, that's got to be the best one, hasn't it? You know. But in actual fact, if you wade through it, you'll eventually come to the definition that we use, which kind of sets everything up. You know, living organisms are defined as those that have the attributes of reproduction, growth, and metabolism. So that's what we mean by life. That's what we're talking about in the context of this evening. And I want to just to step back and think about life for a little bit, and to do that, I've taken these posters that are available through the Stargazing Live websites. These were done in conjunction with us, and you can download them. They come in 2 halves, so there's part 1 and there's part 2. So they're quite big. So I've stitched them together there, and if we look at this graphic, what we've got moving from left to right across the screen is a history of the universe. So time is progressing as we go from left to right. Interesting, when I was putting it together, I kind of remembered that actually there's a mistake on it, or rather not a mistake. There was a refinement in the measurement of the age of the universe that's appeared since we made the poster. And I think that's what science is all about. Things aren't necessarily cast in stone. They're the best evidence and so on that we have at the time, and they evolve. And this is a great example of how things have evolved. But if we think about, well, really anything to do with the universe, but let's just concentrate on life. There, at the start, when we have the Big Bang, when everything formed, there wasn't any life. There wasn't anything. If we look at present day, we have the Earth, and I think we'll all agree it does have some life on it. But at some point in the past, a few billion years ago, that's when life actually began. And so that's what we're interested in, that interface between, when there wasn't any life and there was some life. And if we think about it in the context of the formation of the Earth, I mean, this is the kind of place we know and love. This is a fabulous Apollo 17 image of the Earth, taken 40 plus years ago now. And I think for some of us, it was the first colour image that we saw of the Earth that made us realise just exactly what a beautiful place it is. And that's what it looks like. But that's what it looked like 4.5 billion years ago. And in fact, the geologists call this the Hadean period, after Hades. Now, clearly, you couldn't live on that Earth. Absolutely impossible. There was no life on the Earth. So, in other words, the solar system was formed 4.5 billion years ago. Planets like the Earth were formed, and they looked like this for a while, but then things had to change so that life could ultimately get started. And this is a kind of fairly romantic view about what the surface might look at the interface in this time between the pre-life era and the life era. And Dave's going to give a slightly different perspective on things in his talk. So I just want to remind myself to say that what I'm interested in through the study of comets is that transition between an era when there was no life and then there was life. And by looking at comets, which are remnants of the solar system formation process, we're looking back in time to that material that we no longer have on Earth. It's gone. It's all gone to the reactions and the chemistry and the biology have gone to completion. We have what we have. So we have to go out there and look at comets to see what existed before life got started. But I will just mention Hoyle and Wickramasinghe because they've taken their thinking to a much more extreme levels, and they believe that actually comets brought life to the surface of the Earth. Now, I would say that there aren't really any experiments on the Rosetta mission which are there to address this issue. It's, dare I say, a fringe view, but they would argue very passionately about it. Fred Hoyle's dead now, but Wickramasinghe would argue passionately about it. But most scientists believe that's just a complication too far. So, there are things on Earth called carbonaceous chondrites. This is a meteorite that fell through the atmosphere, and this is the Orgay meteorite. We're celebrating its 150th year of its fall. And most of the people in the community that study these things believe these actually came from comets. So this is quite interesting. If we can go to a comet and make that connection a bit more absolute, then clearly we have the possibility to study these things in the laboratory. And I was going to announce that my head of department had a sample with her for people to witness tonight, but she's forgotten to bring it. Anyway, so a few weeks ago I gave a talk at a conference where we were talking about the connection between Orgay and Rosetta, and at the time this is kind of what things looked like as far as the comet was concerned, and so I was trawling through the web looking for pictures of Orgay. And I came across this guy's personal collection, and the bit on the right there is his sample of Orgay. And so I kind of inverted the image of the comet and put it next to Orgay, and yep, I think that's proof that they must be related in some way or another. And so to Rosetta, the mission that I'm involved with, it's a fabulous mission. It's already arrived. It's already starting to do scientific measurements. It's a two-part mission with an orbiter and a lander. Instruments on the orbiter are already acquiring data, and I hope some of you have seen the images and so on that are coming back. We have an instrument on the lander, the Philae lander, and our instrument is designed to actually take samples of the cometary surface and analyse them and ultimately find out what the comet is made out of. Now, you probably know that over the last few weeks, what we've been doing is struggling over trying to find landing sites. I must say, when we started practicing this process earlier in the year, we kind of imagined the comet might look something like that. So the challenges were there straight away. So we have to consider the shape, the illumination, the slopes, the topography, the fact that you've got to be able to communicate with the spacecraft and all this stuff. It's a very complicated business, but as things stand, a landing site has been selected, which glorifies in the name Site J, and that's where it is on the comet. The bit you can see sticking out, that's the head of the duck, if you like, and then the body's behind it. And actually, the landing area is quite big, and what I've done is just drawn on there a landing ellipse, the kind of area we'd like to try and land in, based on the cross that's put in the centre there. And that is actually smaller than we think we can currently do, but I think in order to avoid some of those features and so on the surface, that's what the engineers are struggling to try and do. And to try and just give a bit of context to the instrument that we built here, this is me in the lab a couple of weeks ago filming Sky at Night, and I'm standing next to one of our laboratory instruments, and that extends off 2 or 3 meters to the left of the slide. It's you can't send those up into space. So I've superimposed on that one of the members of our team, roughly to scale there, and in front of him is the shoebox-sized instrument that we built here. And that is going to do these kinds of measurements in space as the same kind of things that we would do in the lab with this huge, great instrumentation. And it's out there, it's working. I'm afraid this is kind of what we get. We get excited by stuff like this, but that proves that the instrument is working. And I should say that at this very moment, 300 million miles away, we are running the instrument at this very point in time. It's actually collecting samples of the coma gases, and it's going to analyse them, and hopefully we'll get the data back tomorrow morning. Please follow us on Twitter, Philae Ptolemy, and in case you're wondering why the instrument's called Ptolemy, Ptolemy was one of the words in the cartouches on the Rosetta Stone that was instrumental in translating and understanding hieroglyphics. And if you want to perceive that in a more local context, this is the Philae obelisk here at Kingston Lacey House, which is a National Trust property in Dorset. And actually, if you go up to it, it's got hieroglyphics on the side of it. And if you look, it's quite badly weathered, but if you look quite carefully on one of the sides, you can see the cartouche with Ptolemy on it. And that's why we named our instrument Ptolemy. And so I'll end there, but in the spirit of a campaign we're doing, for a promotional campaign for students of the OU, I mean, there's a thank you and there's a landing on a comet thank you. So please follow that. And I would also point to one more thing that we're doing as part of World Space Week. We're doing a Twitter question and answer, Ask the Expert session on Friday this week, I think from 2 until 3. So if you've got extra questions or things you think about afterwards, we're going to be online to answer some of those then. Thank you. So we're going to take a few questions now, but we are very time bound. So if people want to ask questions, please wait for the mic. Ask anything. Oi.
How much gravitational pull has the comet got to give you for landing?
It's a tens of micro, G. So you know, if you standing on it and you sneezed, you would probably never go back again. Yes, it's a very tricky engineering problem. The thing is about a comet, there's hard bits and there's soft bits. And if you land on a hard bit, you're likely to bounce off. And if you land on a soft bit, you might sink. But the lander has been designed with all kinds of features to actually anchor itself down once it lands. You know, it has explosive harpoons, it's got screws in the feet and all this kind of stuff. But it'll hit the surface, hopefully, at something like, if you imagine a sheet of A4 paper landing on a desk, that's kind of what the pressure, what it will feel like. So,
because I was thinking if you're going to start trying to push things down, it'll then push the probe up.
We have thought about that, we have worried about that, but you know, we keep our fingers crossed, you know, in the best spirit of exploration.
Thank you.
Is the comet rotating?
Yeah, it's rotating. It rotates about once every 12 hours or so, and it's interesting when we're actually going to try and land on it. We might be, if we go to Site J, we'll be ejected 7 hours before landing. So you can imagine the comet's actually rotated quite a long way. You know, you can't really see the landing site when you actually eject.
From the sizes you suggested, it sounds like that landing site is not much bigger than this building. Is that about right?
The circle, well, the certainly the ellipsoid would be, yeah, it's a few hundred metres long, but the actual official landing site is a circle of 500 metres radius. But I think it has to get down further than that.
So that sounds like a site about the same size as the OU campus.
Yeah, but I mean, that was what we worked with during landing site selection because we wanted to look at bigger areas. The plan was then to study the areas in greater detail, do the flight dynamics and whatever else, and then to bring that down. Because across some of those areas that we looked at, there are places you just wouldn't want to land in at all. I guess this better be the last one, yeah? Oh.
Could you tell us why this particular comet was selected for the mission?
Do you want the short answer or the long answer?
Short answer.
The short answer is a really fabulous comet, and we knew it wasn't a funny shape or anything like that. There's a historical aspect to this. We designed everything for going to a different comet, and unfortunately the launch before the one that we were due to go on had a failure, and the Ariane program was put back a year. And so, of course, the comet we were going to go to was long since not possible to get to, so we had to rethink it through.
Thanks very much, Ian. So, vote in the room. Are we leaving the comet model here, or am I taking it away? What do you think? Okay. Can I now introduce Professor David Rothery? David works on both terrestrial volcanoes and extraterrestrial planetary surfaces, lunar surfaces, and he will be talking on moons.
Thank you, Simon. I was originally invited to come and talk about signs of life on the moon, which would have been far too short a talk. So I suggested this title instead. Very appropriate. I've been thinking about moons since, I remember it very clearly when Voyager had its last flyby of Neptune in 1989. I thought, let's write a book about this, so I did. And then we had the chance to produce a Moons MOOC last year, which was a lot of fun. Anybody here do the Moons MOOC? It's running again in February. Okay, so search for life on moons. You might not think of moons as being particularly habitable places. I mean, our moon isn't a good place for life, which is why I changed my title. But what does it take? What do you need for a planetary body to be habitable, to be suitable for life? I mean, do you think you need an atmosphere? Do you need to have oxygen? Do you need liquid water? Do you need sunlight? Do you need a source of energy? Which of those do you think are essential requirements for life? Well, here's what I think. You don't need an atmosphere. You don't need organisms breathing oxygen. We do, as far as we know, need liquid water. It's a wonderful solvent. All cells depend on water and so on. So you need temperature where liquid water is going to be available. Sunlight. Plants depend on sunlight. No plants, we'd starve. Well, fine. But there are ecosystems on the Earth which don't need sunlight. You do need an energy source, some kind of chemical gradient that life can grab hold of and use for its metabolism. That's all you need. You need water and an energy source, fundamentally, for life. And we do have water, and we do have energy sources inside certain moons, which is why moons are good candidates for life. And here's an environment on Earth. It's the floor of the deep ocean. This column here being built up by chemicals precipitating is a metre or so long, and this is the plume of turbid water with precipitates forming in it. These are black smokers on the deep ocean floors, and there's white scum around there, which is bacteria. There are a few shrimp and crabs and things scavenging around, feeding on the bacteria. There's a whole ecosystem down there that's independent of sunlight. And this is a favoured environment for where life on Earth could have first begun. Ian showed a picture of kind of volcanic springs at the solid atmosphere interface, but put an ocean in between, you're protected from horrible ultraviolet sunlight or other kinds of harmful radiation, and you can start forming life even when the Earth is still being bombarded by quite a lot of meteorites if you're down the bottom of the ocean. And if you look at the phylogenetics of life on Earth, the last common ancestor we can find is an organism that lives in hot environments like this and doesn't breathe oxygen either. So this is a good setting for life to begin on the Earth, and we've got settings like that, we think, inside various icy bodies. So if life could begin on the Earth, it could begin inside these icy bodies. So these are called, there's chemical energy there at the interface, and these things are called hydrothermal vents. Mars today, bone dry, with a few trickles of water coming out now and then, but the surface is certainly pretty hostile for life. It's bathed in UV radiation. There might be things underground if you dig for them, but it's worth looking for life on Mars, don't get me wrong. But if we want to find a complex ecosystem, we're far more likely to find one inside an icy moon, I would argue, than inside Mars. Icy moons have internal oceans. Here's a cross-section for a Ganymede. This in the middle is meant to be its iron core. There's the rock. And everything above where I've got my cursor is water. Some of it is solid water, that's ice. Some of it is liquid water. Now, inside a body with as much gravity as Ganymede, the ice can take various phases of different densities. And on this model, which only came out a year or so ago, there are oceans at 4 different depths. So in any of those, you could have life, especially the lowest one where the ice is sitting on top of the rock is more chemical rich. So that you could have life inside a body like Ganymede here. Now, that deepest ocean would be very hard to get down to. So there are other moons which have much more potentially accessible life. But just for scale, it's bigger than our moon, slightly smaller than the planet Mercury. This is a big body. Thank you. So here's Europa, which is about the size of our moon. We know from its density, it's probably got an iron core, then rock, then 100 or so kilometres of water. We don't know how much is solid, that's to say ice, and how much of it is liquid, but we're sure that some of it, most of it, is liquid water. The way it interacts with Jupiter's magnetic field, for example, and we can see clues on the surface that the ice has broken apart. So down here on the interface, 100 kilometres below the surface, we could have hydrothermal vents. We can also get the surface like this. Why not hydrothermal vents like this on the floor of Europa's ocean? We know it's hot inside, it's tidally heated. We could have hydrothermal vents there supporting an ecosystem that doesn't need sunlight, doesn't care whether there's an oxygen atmosphere above the icy surface. I mean, there isn't. You don't need it. You can breathe methane or whatever. You can metabolise without the use of oxygen. So as well as the hydrothermal vents, if life began there, it could find its way to the surface in cracks. The surface ice breaks apart now and then, and life could have evolved into photosynthetic life forms inhabiting these cracks. So you've got an ecosystem potential on the floor of the ocean and in these ephemerally open cracks. So there could be life in cracks. So here's a view of Europa's surface seen from above. It's 100 kilometres across, and this is a crack which is opened and closed, and every time it closes, it squeezes some slush out and builds up a ridge either side. Go to one of those cracks when it's open, you could find the life in the ocean. Go to a crack when it's squeezed shut and scrabble around in the slush that's refrozen, you could find entombed dead organisms. So here's what could be inside one of these cracks. Some plants clinging to the walls, some planktonic things which get sucked up when the crack opens and pushed back down when the crack closes, things which crawl. So you could have photosynthetic life near the surface as well as chemosynthetic life at the vents deep down. And we can tell that the ocean is dynamic because look at an area like this. You can see places where you've got rafts of ice which have just barely broken apart. But over here, the ice has been completely disrupted and has refrozen in between. That ocean is occasionally exposed to space, we think. Okay, so Europa is a big one. If you want to get down to the surface of Europa to look for life, it's quite a challenge, but I'll come to a possible solution at the end. But Enceladus, a satellite of Saturn, nearly 500 kilometres in diameter, it's a much easier target to go for because can you see these plumes here? Below the South Pole, water is being jetted to space. Not as liquid droplets, it freezes straight away. I mean, the surface temperatures here are minus 160 centigrade, so it's way too cold at the surface for life, but once you can get warm water up there, you're okay. So we could have, there's an ocean clearly inside Enceladus, which is venting to space. All you then have to do is fly a spacecraft through that plume and sample it. And now here's a wonderful close-up of these vents jetting a couple of 100 kilometres into space from these cracks near Enceladus' south pole. Fly through there with the right instruments, you can find life. Because if there's life inside, you should find it being jetted into space. Well, there's a mission there called Cassini, which has flown through the plumes, but it wasn't equipped to look for life. Nobody suspected this when Cassini was designed. So that's a kind of model through Enceladus, a rocky core, an ocean which may not be global, just a sea over the South Pole, and tidal heat, disturbing things, keeping the water warm enough, and venting to space. So just to look ahead to where we hope to go in the future, nearly 2 years ago now, ESA announced an instrument suite for its Jupiter Icy Moons Explorer, a mission called JUICE, which we hope to have Open University involvement in. It will orbit Jupiter. It will study Ganymede in detail. It will have a few flybys through flybys of Europa as well, looking for life on Europa. And this was going to be my last slide until last night when this news item came to my attention. This is a NASA proposal that's just received $100,000 as a preliminary study to develop this concept further. It's a CubeSat. It's 3 things as big as a packing case, 3 or 4 things as packing case size bolted together, which it would go to Jupiter, orbit Europa, map its gravity field, and then open up and just shower these things down onto Europa's surface. These are called ChipSats because they're pretty small things. Give you an idea of scale. They're smaller than this wonderful book, Planet's a Very Short Introduction, $7.99 from Amazon, which I wrote. But probably smaller than my iPhone. What they are like in size is the thickness of just a few individual Moon Trumps cards, which you can get from the OU website. And these things will be equipped with sensors just to do 1 or 2 specific tasks. You could kit these out to sniff out molecules to do with life. Land them, ideally, some would land beside some of these recently closed cracks and look for signs of organic processes having gone on Europa. I mean, Europa's hard to land on because it's got no atmosphere, you can't parachute down. Shower a few of these things down there, robust, some will survive landing on the surface. Maybe that's the way of the future. Shower a load of ChipSats onto something like Europa to see if there's life. I'll have retired by the time that happens, but hopefully some of you won't have. And I think let's go looking for this life out there, because I want to know, if life began on the Earth, did it begin anywhere else? If we can find that life began independently of the Earth on one other place in the solar system, then hey, all these exoplanets out there that Carol's going to talk about, surely life has begun on suitable exoplanets as well. But at the moment, all we've got to go on is one Genesis on the Earth. If we can find a second Genesis inside Enceladus, inside Europa, that's a fundamental change in our philosophy. Thank you. Sure. Any questions? And please wait for the microphone.
Is there any problem with like bacteria from our world, being put onto a pristine environment?
Very much so. It's very hard to get a lander on Mars clean, a lander on Europa clean. If you fill one of these things with ChipSats, look at all the surface area on all of these little things. You've got to have them completely, we can't have them completely devoid of life. As devoid of life as you can before you launch. And you've got to hope that most of the things die en route, but some will survive. We know microbes can survive in space. There are rules in place by an organisation called COSPAR, Committee for Peaceful Use of Outer Space. I forget what the acronym stands for. And there are rules which say anywhere you send a spacecraft from Earth, there must be less than a 1 in 1,000 chance or 1 in 100 chance of contaminating it. Because it recognises that ultimately, if we send something to another planet, we're going to contaminate it. Now, you may have ethical reservations about putting Earth microbes in an environment where they might live. It will certainly be harder to study the Europan biosphere if we've taken earthly organisms there as well. But ultimately, if we're going to explore space, we cannot avoid contaminating these other bodies. But on the other hand, nature might have done it already. We've got, as you heard in Ian's talk, we've got meteorites on the Earth which have come from Mars. There'll be bits of Earth rock which have been knocked off the Earth and found their way to Mars. So Earth and Mars have been exchanging bodily fluids for the past 4.5 billion years. So life on Mars could have come from Earth or vice versa. It's harder to get from Earth to Europa. So it's likely that life on Europa is independent of the Earth, but we need to check that it hasn't got there accidentally. And we certainly don't want to deliberately, not deliberately, but accidentally contaminate Europa by sending a dirty spacecraft there. There's a question here, if we have time.
You mentioned water and a source of energy.
Yeah.
And saying, well, that's the prerequisite for life. But we're carbon-based life forms. Is there any chance that there's another element that life is based upon. You say that, when we've gone there, we weren't looking for something. Is there a danger that we're not looking in the right place?
There is a risk. You're quite right. But I think we have to deal with life as we know it, because we know life based on carbon and using water can exist. You can construct life based on silicon, but it doesn't bond to as many elements or germanium as carbon does. You can look for solvents other than water, but they don't seem to be as good. So let's begin at least by searching for things that we can recognise as life. But I don't have a closed mind. There could be other kinds of life, but people have looked at how life might work, can't come up with anything better than complex carbon-based molecules, and anything better as a solvent than H2O. So we're probably looking in the right places, though possibly not the only places.
Thanks very much, Dave.
2 minutes, apparently. Yeah. Any more questions?
Oh, one more.
Okay.
A little bit off the wall. Why would you not accept that we have already landed on Mars?
Why would I not accept that what hasn't already landed on Mars? Life
Well,
from Earth.
Yeah.
We could have terrestrial life on Mars carried there on our spacecraft which weren't clean enough, or carried on meteorites from Earth to Mars.
No, I'm talking about human life that have been sent up from this planet up onto the Mars, where there's underground cities. And this is all done by USA and NASA. We have actually been on Mars since well before the Second World War.
I really don't think there was the technological capability to do that, or that any conspiracy like that could have been kept secret had it have happened.
I could go more, but I'll leave it at that. But it's quite deep. We are actually on Mars. Thank you.
Do we want to take one more? Lady behind?
Sorry, I just have one question. The chips that they're thinking of sending out, what are the chances of them actually landing without being smashed and being able to send back?
I think the idea is that they would be robust and that 50% would survive impact. If you're sending out several dozens, then you're going to get plenty of data back. We can make bunker-busting bombs, which will go through several stories of underground bunkers and count how many floors they're going through before they explode to kill the bad guys. So we can build technology, it's the war dividend, we can build technology that will survive enormous decelerations and still work. So it can be done, but my understanding of a ChipSat concept is that they are sacrificial. Some will survive, some won't.
Okay, thank you.
There is more research going on at the Open University, actually building mass spectrometers that go into artillery shells. I've seen in the entrance to one of the buildings is actually an artillery shell which has been hollowed out. So there is research going on that. I'm just going to, it rotates once every 12 hours. Can I now introduce Dr. Carol Haswell? Carol's an astronomer who works with telescope observations, and she's going to talk about exoplanets.
Thank you, Simon. I have to say at first I haven't brought any props with me, so I'm very glad I've got Ian's duck to keep me company up here. Nor do I have anything to sell. Obviously, I failed to prepare. However, in mitigation, I think I do have the best topic, because I think if we want to find life outside the Earth, the place to look is exoplanets. Exoplanets are planets which are orbiting around stars other than our own sun. Okay, so I'm going to start by setting the scene, and this is an artist's impression of our own Milky Way galaxy. I'm an astronomer, I work with light, and so, I'm just wondering, so what we collect as astronomers is light using telescopes. So if we were to observe a galaxy like the Milky Way, what we would see is a lot of light, and that light is coming from stars. This is probably obvious, but I thought I'd say it anyway. Stars are much bigger and much brighter than planets. So as astronomers, it's fairly easy to study stars. Studying planets, which are not in our own solar system, is rather troublesome because they're small and they're dim, so they're difficult to study. The difference in brightness between the Earth and the Sun is a factor of about 10 billion. So you're looking for something very, very faint next to something much brighter. So that presents obvious problems. So I'm just going to tell you a little bit about stars that we're going to need later on. So this is probably the most important diagram in astronomy. This is the Hertzsprung-Russell diagram, and it's a graph of, on the y-axis, the brightness of stars, on the x-axis, the colour of stars. And almost all the stars in our galaxy that create that beautiful pattern of light that you saw in the artist's impression fall along the diagonal stripe up the middle of that diagram. And these are so-called main sequence stars. Our sun is an example of a main sequence star. And what all these stars have in common is that they're converting hydrogen to helium at their center, and this creates the energy that produces the sunlight and the starlight that creates light on the planets orbiting around the star. Our sun is about a third of the way up that stripe, and there are actually more stars lower down that are smaller, lower mass, fainter and redder. And then as you go up towards the top of that stripe, you've got more massive stars that are bluer and brighter. Okay, one of the things that we've learned in the last 20 years, which I think is really remarkable, is that we now know that there are actually more planets than stars in our galaxy. So when you look at the light in a galaxy, you see the starlight just because the stars are bright. But we've now done enough work on nearby stars in our own galaxy to know that actually, in general, stars do have planets orbiting around them. So there are lots and lots of planets in our galaxy. We don't know about all of them in detail. The assertion that I just made, that there are more planets than stars in the galaxy, is based on statistics. We know of about 2,000 planets in detail, and these have been studied by astronomers over the last 20 years or so. We know of 1,137 planetary systems, or at least we did on the 9th of September. So these numbers are about a month out of date. So we're probably up to about 2,000 planets now, because there's quite a large number of astronomers in the world who are constantly studying, looking for new planets, and there are new announcements coming out every day. So we know in detail of about 2,000 exoplanets orbiting around stars other than the sun. And so we now know that planets form with stars. There's no special requirement at all. 20 or, well, more than 20 years ago, it was possible still that our own solar system was unique. Something special had happened to the sun in its early history that created the material that then formed planets. But we now know that planets do generally form with stars. There's no special requirements. So we would expect the other stars, like the sun, to have planets also orbiting around them. Now, I should probably just tell you a little bit about how we found these almost 2,000 exoplanets that we know about, because I've told you that it's very difficult to see planets because they're dim. So both of the main ways that we've detected these planets depend on actually studying the light from the star and observing in the light from the star subtle effects due to the effect of the planet on the star. So you can actually, you think of planets orbiting around stars, but in fact, from the point of view of the laws of physics, both the star and the planet have mass, and they both orbit around their common center of gravity, which is much closer to the heavier star than it is to the light planet. So the star itself has a little orbit, which you can detect by looking at the light from the star and looking at the Doppler shift of that light. And then there's another even more simple way of detecting a planet around a star, which is if you happen to have a planetary system that's lined up so that the orbit of the planet happens to take the planet right in front of the star from our point of view, then the planet gets in the way and blocks some of the light. So you can actually see the star get dimmer every time a planet gets in front of it. So these are the two main ways that we've detected the almost 2,000 exoplanets that we know about. Okay, so I'm now going to change gear a little bit and go back to a brief history of life on the Earth. So I'm revisiting some of the points that Ian and Dave have already made. So from about 4 billion to 3.8 billion years ago, the Earth was being bombarded in an early period of its history called the Late Heavy Bombardments. It was being bashed into by all sorts of stray bits of rock and asteroids that were chaotically orbiting around in the solar system. So at this point, the Earth was probably not habitable. But the interesting thing is, rather promptly, on astronomical timescales, a mere 300 million years after the Late Heavy Bombardment, we can see evidence that photosynthesis was already happening on the Earth. So that implies that life got started really very quickly after the Late Heavy Bombardment started. So this means that probably you don't require very special circumstances for life. Now, the rather more pessimistic thing is that complex life, of the sort of thing that you and I, trees, cats and dogs, that happened rather late. And this is at the very other extreme of the history of life on Earth. So it was about 600 million years ago that the first very complex life happened. So that may require rather special circumstances. So from analogy with that, it seems that probably life may be common on planets elsewhere in our galaxy, but complex life may be rather rare. Okay, so Dave told us that we need a source of energy and liquid water for life. And I told you about the different kinds of stars. Where you would need to put a planet in order to have liquid life on its surface depends on the type of star you're orbiting around. So the big hot blue stars have a habitable zone that's fairly large and fairly far away. The more plentiful, cool red stars are dimmer, and so you need a planet to be closer in to have a temperature consistent with liquid water. But it's more complicated than that. You can't just put the planet in the habitable zone and say it's going to be a habitable planet. It's much more complex than that. And as we know from our own solar system, the difference between Earth and Venus is dramatic. And it depends, a lot depends on the atmosphere and the clouds, whether you have a dry and toxic environment like Venus or a wet, habitable environment like the Earth. So clouds can help, as they do on Earth, but if you have too many clouds, they can trap heat and cause a runaway greenhouse effect. So it's really rather complicated to assess whether a planet is habitable or not. In the future, with more powerful telescopes, we may be able to make observations which will allow us to identify individual chemicals in the atmosphere of planets. And this gives us the potential to actually say, is there life now on the surface of this planet that we're observing? So, for example, on the Earth, we have oxygen in our atmosphere. Oxygen is highly reactive, and we only have oxygen in our atmosphere because it's being constantly replenished by the processes in plants on Earth. So if we were to be able to detect oxygen in the atmosphere of an exoplanet, that would be a so-called biomarker and give us a strong steer that perhaps there is in fact life on that planet. Now, finally, I'm going to, as promised, tell you a little bit about some work that we did here at the Open University. So I told you that most of the stars in the galaxy are along that diagonal stripe in this diagram. All of those stars will eventually run out of fuel, and almost all of them will end their lives as white dwarf stars, which are in the bottom corner of that diagram. And those stars are no longer doing nuclear reactions. They're just dying embers that are cooling like coals left over after a fire. And it turns out that planets can survive around compact stellar remnants like that. And surprisingly, the way that white dwarf stars cool actually leads to conditions where you could have habitable temperatures on planets for up to 8 billion years as the white dwarf is cooling. So we did a little bit of work just examining this using the real spectrum that you would expect from a white dwarf star. And we were able to calculate that if you put a planet in the right place, you could have this persistent habitable zone in which you have photosynthetically useful light that plants could use to generate energy, while simultaneously not having too much damaging UV radiation. So this is quite a sort of an optimistic, sort of very long-term picture that as all of the stars in the galaxy burn out, we could nonetheless have a galaxy that's teeming with life on planets around white dwarf stars as we look sort of 10 billion, 20 billion years into the future, the prospects for life in the galaxy are actually rather promising. So, do we have questions? If you have a question, you need to wait for the microphone. Yes, there's one here.
The planets that you're finding on the stars, how far away are the stars from us in light years?
Ah, right. Handily. I happen to have so this is a sort of schematic diagram of our Milky Way galaxy, and there's a scale there in light years, and the distance of our sun from the center of the galaxy is indicated. So the planets that we find, their distance depends on the method used to find them. So there's a little cloud of sort of greenish points there that are clustered quite close to the sun. And those are the ones that have been found by the Doppler technique, where we're looking at the motion of the star caused by the larger motion of the less massive planet. And to do that, you need a fairly bright star because you have to spread the light out very, very widely. So you need a bright star to be able to do that. Then there's a sort of a slightly larger cloud of red points, and those have been found by transit surveys. So at the Open University, we are involved in the SuperWASP project, which has found quite a number of transiting planets. I think we're up to almost 200 now. And those planets are around stars that are slightly more distant from the sun, because you just have to collect all the light from the star to find them. You don't have to do the very precise spectroscopy. And then many more have been discovered by a NASA satellite called Kepler, which pointed in a particular direction and made very precise measurements, again, looking for planets that are getting in the way of the star and causing a transit signal where the light dims. And because it's pointing in a particular direction, it's actually on average looking at fainter stars, so those are dimmer. So I've sort of schematically indicated those with the blue dot. And then there's another method I haven't told you about, which uses gravitational lensing, and that tends to find things just this side of the center of the galaxy. So that's probably a more detailed answer than you wanted. Yeah. Yeah, just wait for the microphone.
Would there be lots of planets going around every one star? Like, how many on average? Would there be like 8 or 9 like in the solar system, or would there be lots more?
That's a really good question, and that's something that astronomers are working on. So we don't really know at this point, because all of our techniques require certain things in order for us to be able to find the planet. So for the transit technique, we need the planet to get in the way. And if you were to look at our own solar system, the planets are aligned more or less in line with each other, but not quite. So there are quite a few systems where there's sort of up to about 5 or 6 transiting planets that have been found in the same system. But you don't really know if there might be some that are just misaligned a little bit, so they're just missing going in front of the star. And similarly with the Doppler shift technique, you can detect the very massive planets that cause a big wobble easily, but there could be less massive planets in the same system that we're failing to detect. So we do know of systems where there are 5 or more planets, but we're not sure really what the typical number is yet. That's a very good question, and you could probably still research on it, when you're old enough to do research at university.
Hi, your research looking at the biomarkers for planets with life seems to be based around oxygen levels. Mm-hmm. If obviously you looked at the Earth, you wouldn't see oxygen levels as much with what we're looking at because it's nitrogen based. Mm-hmm. So are you looking at it with different makeups like nitrogen and carbon dioxide based as well?
Yeah, so what you're doing is you're looking for something that's sort of out of equilibrium, where you've got to have some sort of metabolic process. And I should probably also say that that's not a particular thing that I've worked on. The things that I've worked on are the bits that I picked out, but that's one of the most important general things that people are preparing to do in exoplanet astronomy in the next 10 years or so.
Thanks very much.
Thank you.
We're going to carry on questioning a little bit longer if we can get the speakers. Okay, we've been taking questions on the Facebook page, and some of them have come in through the live stream during the week. So I've got a few here, and I'm going to start off, and then if there are more questions that come out, we'll take those from the room as well. First question. Now that a spacecraft is on the edge of the solar system, could it be used to look at the types of particles, objects, or space there is beyond our solar system and see if there's anything out there that looks like life? Dave, do you want to start that one?
Well, this will be alluding to one of the Voyagers. Is it Voyager 1 or 2 that's left the solar system now? The probe that flew past Neptune in 2009 and sent back wonderful pictures of Triton and so on is now beyond the solar system, and it's still working, but it wasn't equipped to do anything beyond the solar system. It's detecting particles and magnetic fields, and it's not really able to look outwards for distant signs of life. It can look at its immediate environment and see the field strengths. So it's a wonderful old spacecraft still doing stuff, but it's not going to tell us anything about life beyond the solar system.
I mean, it's launched a long time ago, wasn't it?
77 they were launched.
There's a big gap between that and what you're looking at, Carol. How do we look at something between the edge of our solar system and the distances that you're looking at?
Well, as an astronomer, we need light, and light by and large comes from stars. So you can look at what's called the interstellar medium, the material between stars, by seeing it absorb some of the light from distant stars. And certainly some of the molecules that are thought to be prerequisites for life have been detected in the interstellar medium, but I don't think anybody would think that the interstellar medium was a particularly promising place for life because it's so low density. I think you probably need a bit more stuff to get life going.
Okay.
But I think what it shows that if for whatever reasons you wanted to do this, it's going to take you 40 years to get there before you can start looking.
Yeah.
So it's a tricky thing to study by sending a spacecraft.
Yeah, and there's a lot of different ways we could do it. If people have a particular question that's coming out of discussion, just stick your hand up and we'll try and pick it up. Another question that came from Facebook. Can people propose experiments that they would like to be sent onto comets or into space? You want to take that one in?
Well, it's an interesting one because the process that we went through was very formal, and it was the way things were done and the way things are likely to carry on being done if they're done through agencies and whatever else. I think just around the corner there's a new era of entrepreneurs or people who want to utilise space for their own probably commercial ends involving space tourism or whatever. And we can see that's, we're on the cusp of actually seeing some of these things now. And I think that those will give the opportunities for people who want to do scientific research to piggyback onto these missions. And I think it'll open up certainly great new possibilities for research projects.
Okay.
But if you want an instrument to do so-and-so on a spacecraft, you probably have to be able to build that instrument yourself, because you can't normally buy them off the shelf. We're pushing the edges of technology with these instruments.
That's not
true.
No,
Okay.
CubeSats now, you can actually buy the bits and pieces just off the web and you can put them together yourself. No, I think it's entirely possible. It really is just around the corner. I think the question was particularly about landing on a comet or something like that. That is a bit of a tough one for anyone to do, and I think missions like that are going to remain the preserve of European agencies or whatever, because they're just so challenging.
Okay, thanks. I'm going to take another question. We may have covered this one, but let's just do it. Are viruses things that have developed on Earth, or did viruses come from space? It kind of goes back to your talk, Dave.
I didn't mention Fred Hoyle and Wick Ramasinghe.
Fred, sorry. Well, you can talk about it.
I don't think so. Comets can deliver building blocks for life. We have no evidence that viruses, which are sort of prebiotic things, were on comets. So I think they probably began on Earth, but I can't prove it, and it's one of the things we're trying to find out.
I mean, it almost gets a little bit philosophical, that, because, I mean, Dave did talk about the possibility of meteorites from Earth going to other planets. Well, if they do, they will take stuff with them in a fairly sort of randomised way. I mean, in the same way, we're probably somewhat paranoid about bringing samples back from Mars to Earth, which could have, Martian life forms on them. And we'd have all kinds of quarantine procedures and God knows what. Meteorites from Mars arrive when they do, and they come with whatever they've got. So, this is already happening. It's already happened.
Got a question down here in the room?
If comets and asteroids are deemed to be, messengers carrying water or building blocks of life, where did the building blocks of life originate from? What's the latest theories or speculations?
Well, interesting, that probably is much more in Carol's domain than mine. They are made in stars. They are made in the interstellar medium by actually by processes that are fairly well understood, and it's the interesting aspect of how they get transformed from diffuse clouds of stuff. How they then aggregate into a solar system that has a central star and a planetary system. Now, it's interesting, I mean, Carol was talking about exoplanets and whatever else. We tend to forget that actually this phenomenon was discovered in our lifetimes, and most people here, I guess. Several years ago, there weren't any exoplanets. The only planets we knew about were in our own solar system. I mean, now that we're finding them everywhere we look, I mean, it was kind of mad that we would have thought that perhaps our solar system was special. So I think that's the interesting part, is how you convert from the stuff that you start with into what we've got, and that's what people like me study. But if you want an answer about how it's actually made, then Carol's your person.
I'm not sure I'm really your person, but we do have quite a lot of astrochemists here at the Open University who, in the lab, will try and make a vacuum and then try and make some of the molecules that have been seen in the interstellar medium. And they also do sort of analysis of the spectrum of those molecules so that they can identify them in the interstellar medium, as I said before, looking at the absorption of light from background stars. So there's a long list of, I think, dozens of molecules, including sort of things that you need to build amino acids that have been detected in space. And I think it's thought that a lot of them form on little dust grains. So, an atom will hit a dust grain and then sit there bored for a very long time, and then another atom will come along and you maybe get a molecule forming very gradually in that way.
But in principle, what we're made out of is stardust. All the elements in our bodies were made in stars.
Got a question? Oh, down there.
So far you've talked about fairly primitive life forms. Any thoughts about how we would detect whether this life form is, in our sense, intelligent? And how would you know who it was?
Well, Carol touched on whether or not it's difficult to go from microbes to complex life. Are cells going to stick together, give you multicellular organisms? And if that happens, is intelligence going to be a driver for evolution and will self-select and push life towards intelligence? People have famously argued that it only took a few billion years to get intelligent life on Earth to our stage. We could be colonising the galaxy in 1,000 years' time. You can build a ship that goes a tenth the speed of light that will take 1,000 years to get to another star, bootstrap a civilization, and then go on. You could colonise the whole galaxy in 10 million years. Why has nobody else done that? We see no signs of anybody having done this. And this is the Fermi paradox. Enrico Fermi articulated it. Where is everybody? If life is so common, is intelligent life common? And if it is, why can't we see signs of it? It's a big mystery. It could be pointing to the fact that life doesn't get started anywhere else, or it could be that complex life is extremely rare, or that intelligence rarely develops, or that everybody who's intelligent is actually rather stupid and kills themselves before they can start colonising space. But it's a big paradox.
Is it also not possible that there could be some sort of cosmic co-spar agreement not to pollute us culturally with superior knowledge?
Okay, let's take another one from the Facebook page. Are the signatures of life on Mars the same sort of bacteria that's found on ancient Earth bacterial traces? I'm going to allow you to, the plausible deniability of life on Mars there, but is the signature or are the things on Mars like we see in ancient Earth?
Well, I mean, it's an active area of research, and there are new missions going to Mars all the time, some of which are going to try and address this issue. It's been discussed already about the fact that it's a little bit tricky. We can go to Mars and we can study it in a very kind of black and white sort of way. We can find out what it's made of, whether there are organic compounds, whether there's a water cycle, whatever. If you want to know about life,